Alright, so today we are going to talk about interconnection architectures. As we discussed, if you want to scale to a very large number of nodes, you have to have a distributed memory architecture. Shared memory architectures don't scale to very large number of nodes. So what are the different kind of interconnects that we can set up, right? So let's say you are trying to set up an interconnection architecture for your system of nodes. So let's start with two very basic ones, and let's see what are the advantages and disadvantages of these. So one is a simple linear array, right? So let's say 1, 2, 3, 4, 5, 6, 7, 8, right? So this is a linear array, and another is a clique, right, or a fully connected network. So what is a fully connected network? Yeah, so you get the idea, right? I'm not going to draw the whole thing. It's going to become very messy, but you get the idea what a fully connected network is, right? Every node is connected to every other node, right? So which one would you pick? If you were to set this up, let's say in your own lab, a distributed system, you had 8 nodes and you wanted to connect them up, which one would you pick?
First one.
Okay. Now let's say that I tell you that instead of 8 nodes, you have to set up a network with 800 such nodes. Now which one would you set up? Cost. So, okay. What is cost?
The interconnection wirings, whatever we are making to connect each and every node with each other. So
Yeah.
maybe that would increase the cost.
Yeah. What else? Anything else? So you are going in favor of this one, right? The linear array, because the number of links, the number of interconnects that you have to set up, the links you have to set up is not too large. Good. That's one measure. What is the advantage of a fully connected network over a linear array?
Reduce complexity, maybe.
Complexity. Complexity is high.
It will take less time to.
Yeah. Latency.
Yes.
Yeah. So one of the measures we said was number of links. Another one we said was latency, right? So clearly this one is good in terms of number of links, right? The cost. In some sense, I mean number of links is cost in some sense. Cost can mean a lot of different things, but one of the factors that affects cost is the number of links, right? But the problem with this is latency. What about the second one? What is the problem with this?
Number of connections are high.
Number of links, the cost is very high, right? But what about the latency? The latency is great, right? I mean, anybody you want to send a message to, it's just one hop away. That's it, right? Okay. So yeah, these are two extreme cases, right, of interconnection networks. So ideally, you would not set up either of them if you had to set up a network with 800 nodes, right? So we are going to study different interconnects, and we are going to talk about different metrics, right? Different things to consider when you set up an interconnect, right? So obviously, every network has its advantages and disadvantages. First of all, let's talk about the metrics, right? So what are the metrics? So one is the number of links. So we are definitely bothered about the number of links, right? That determines the cost. Another is the diameter. Diameter is what determines the latency, right? Diameter is the distance, the shortest distance between the two furthest nodes, right? The maximum shortest distance in the network, okay? And a third metric we are going to be interested in is degree, maximum degree. This is important, right? Just imagine you are setting up a node over here which has 800 incoming links. How are you going to build such a node? Every node has 800 incoming links, right? So these are challenging things. It's okay as long as you're dealing with tens of nodes, but we are talking about going to the order of 100,000 nodes, right, in supercomputers. So you cannot build such networks, right? Okay. And the fourth metric we are going to be interested in is something called bisection width. What is bisection width? So yeah, the other ones are obvious. So bisection width, let me define it more formally, right? So this is the minimum number of nodes to remove that cause the network to be separated into two equal halves. Okay. Let's come back to this, right? Let's look at the linear array. So how many links do I need to remove in order to separate out the network into two equal halves, roughly equal halves? So these are 8 nodes. So if I cut this over here, right, if I remove this link, I'll have one separate network over here of 4 nodes and one separate network over here of 4 nodes, right? So in a linear array, you only need to remove one link, that's it, in order to separate it out. Okay, so the bisection width of a linear network is 1. What about the completely connected network? What is the bisection width here? 800 into number of nodes. We can be a little more careful.
800 by 2.
Okay, let me cut it here, right? Actually, no matter which cut I take across two separate 4 nodes, it's symmetric, so it's going to result in the same number of nodes. So I have to remove all the links which are cutting this blue line. What is the number of links cutting this blue line? Well, there are half the nodes on the left hand side, so that's 400, right? And they are connected to all the nodes on the right hand side, right? Which is 400 times 400, okay? So that was just to give you an idea of bisection width.